Hi everybody, Professor Burns here. We are looking at our last unit in differential equations, and in this unit we're going to be focusing on systems of differential equations. So in this first section we're looking at a few examples of modeling, and the main one I want to look at is called the predator-prey system. If you were to take a biology or an ecology class, you may talk about how the interaction of two animals, one being a predator, one being a prey, how they may affect their population growth. So it says, suppose that the population for R of t represents your prey and W of t represents the predators. So think R like for rabbits maybe and W for wolves. In the absence of predators, so supposing there's no wolves and we're just looking at the rabbits, we would have an ample food supply that would support exponential growth of the prey. So the differential equation in that scenario would look like this. dr dt, so the rate of change of the prey, is equal to kr, where k is going to be some positive constant. On the other hand, if we didn't have prey, the predator population would eventually die out because they wouldn't have anything to eat. So for the predators, we could say the rate of change for their population, dw dt, we could say is negative rw. Again, r is a positive constant, but it's negative because the population would be declining. Now, if both species are present, they're going to interact with each other. And so it says, assume that the principal cause of death among the prey is being eaten by the predator, and the survival rates for the predator depend on there being a supply of prey. Also assume that the two species encounter each other at a rate that is proportional to both populations and is therefore proportional to RW, the product of RW, that's called the interacting term. You don't need to get too in the weeds with all of this. You guys aren't science majors, so this is not something you need to worry too much about, but I want you to see what this system would look like. So in this case, when they're both present, we would say dr dt is equal to kr minus arw. That's called the interacting term. And then likewise, dw dt, so the rate of change for the predators, would be negative rw plus b times rw, so the interacting term, where kr, a, and b are positive constants. This is called the Lotka-Volterra system, and this was first published, I think, in the early 20th century by these mathematicians. You don't have to memorize this or anything like that. I just want to do a little practice kind of working with these equations to see how they operate. So let's do a little example here. It says, suppose a predator-prey system is modeled by this system of differential equations. This time R is the prey and F is the predators. Okay, so they'll tell you which is which when you see these problems. It says to interpret the interaction term. So first of all, let's identify what they are. So for the rate of change of the prey is R, don't forget. Let me see, let's write that. So the prey interaction term, the term for the prey is going to be the negative 1.2 RF. And so because it's negative, what does that indicate? That indicates that the prey is going to be declining or decreasing. And that should make sense because if the predators are in the population, the prey would be going down. That's the idea. They're going to eat the prey. So we'll say because it's negative, because that constant there is negative, that means that there is a decreasing population due to the interaction. We'll say it that way. So you want to look at what the sign is for that coefficient. On the other hand, what's happening with the predators? So if you look at their interaction term, that is the, right here, the 0.9 RF. Now because that's positive, the opposite is happening, right? So because of the involvement of the prey in the environment, or the existence of the prey in the environment, the predator population is going up. So for that one, we're going to say it's positive, which means that, on the other hand, it's increasing in population due to the interaction. Now, there are a couple of other scenarios that may come up from time to time when you see these interaction terms. One is that they could both be positive. So if both terms were positive, that's called a cooperating system. And so they're both increasing population for whatever reason. Again, I'm not a biologist, so I'm not sure. I'd have to find an example of what sort of populations would be both increasing if one's a predator and one's a prey. But I guess that could happen. And then opposite would be true as well. So if both were negative, that would be a competing system. And I think in that case, it maybe they're competing because of resources, the environment, but in that case, both populations would be declining. All right. So the next part says, find and interpret the equilibrium solutions. So equilibrium, that would be, equal to 0. That'd be where we have a stable system. And so what we're going to do to figure out where this occurs is we're going to set both of these equal to 0. So we're going to get 2 solution points here. Let's do this. Let me go ahead and set the first one equal to 0. So I've got 2r minus 1.2 rf is equal to 0. And I'm just going to factor an r out. So that leaves me with 2 minus 1.2 f equals 0. So I'm going to have 2 solutions here. Obviously, r equals 0 is a solution. And then if we set 2 minus 1.2 f equal to 0, we would get a solution of 1.67. Now, so these are half of my solutions. Let me go ahead and plug these into the other equation. So remember, my other equation was negative f plus 0.9 rf, and we want to know where that also equals 0. So I'm going to do the same thing. I'm going to factor out, they have an f in common. I'm going to take a negative f out. So that leaves me with 1 minus 0.9 r. All right, and then let's think about how each of these solutions will affect what's happening. If r is equal to 0, then the only way that this expression, this equation, could be equal to 0 is if f were 0. So let's jot that down. If r equals 0, then f would have to also be 0. So that means one of my solutions is going to be 0, 0. Okay, how about the other solution we had? If f was equal to 1.67, if you substitute that into this equation and solve for r, you're going to end up with 1.11. So my other solution is, and by the way, let me clarify, we're doing r comma f is the way I'm writing these ordered pairs. Then this would be 1.11 comma 1.67. So those are going to be my 2 equilibrium points. Now, what does this tell us about the system? Well, if 0, 0 is our equilibrium point, that just means that if there's no wolves, or I'm sorry, whatever these were, yeah, I guess they were wolves. No wolves, if there's no rabbits, the populations are not going to be changing at all. So let's just kind of write that. It's kind of a trivial case, but it's one to consider. If there are no rabbits or wolves, obviously there's no change to either population, right? Because if you start with nothing, nothing's going to change. So populations are staying steady and not changing. Okay, now what about the other one? That one's a little bit more interesting. So if we look at the other solution, in this case, what we're saying is if we have a population, so a population of 1.11, and I didn't say it in the problem, but I think this was actually times 1,000. These were in thousands, but whatever. A population of 1.11 rabbits will do what then? So if the population is 1.11 for the rabbits, that will maintain or sustain a population of wolves at 1.67. So in other words, the wolf population will be stable if we have a population of 1.11. So population of 1.11 rabbits. So let me read what I'm writing. A population of 1.11 rabbits would sustain a population of 1.67, again, times 1,000 wolves, I guess what we were looking at. Okay, now last thing, let's take a quick look at the phase portrait and see what's going on. Okay, here we go. I've got this pulled up in GeoGebra, and this picture is fine, but I also graphed this in Wolfram Alpha, and I kind of like this picture a little bit better. I think it's a little easier to see what's happening at the equilibrium points. Let me see if I can zoom in just a little bit. Maybe I'm not able to enlarge. I don't know. I don't use Wolfram Alpha much for the, no, I have to go pro. I'm not going to do that. All right. That's okay. Let me go ahead and just show you what's going on though. We've got 2 equilibrium points, don't forget. Remember that one was at 0, 0. That was right. It's in here. So I can't click or plot on this, but what I want you to see is that the system is stable at 0, 0. And then again at the point, remember it was 1.67. That would be right here where my arrow is. Hopefully you can see that. So notice that we have 2 equilibrium points at that location, at those 2 locations, and that means that neither population is changing at those locations, or if we start out with those values. And I believe, let me go back to the notes. I think I put a picture from the textbook in your notes. Let me see if I can pull that back up here. Here it is. I didn't put it in your notes, but I did put it in mine. So here it is if you want to screenshot it. And I wouldn't ask you to draw this by hand necessarily, but what I just wanted you to see was at this location and at this location, those are your 2 equilibrium points. And so your population for both the rabbits and the wolves are stable. They're not changing at all at those 2 locations. And we'll do a little more practice with this in class, just kind of get used to seeing what happens at these equilibrium points. But I think that's all I wanted to do in this lesson. So bring your notes with you, and I'll see you tomorrow.